Another commonly used statistic to check the goodness of fit or the predictive power of any binary classification model like logistic regression, etc., is the ROC curve, also known as the receiver operating characteristic curve, and more specifically, what's the area under the ROC curve. So what is an ROC curve? So in this particular video, I'm going to dive deep into ROC curves, how they are calculated, how they are interpreted. So very simply said, the ROC curve is basically the trade-off curve between sensitivity and 1 minus specificity for each probability value cut point that we can take between 0 and 1. For example, in my previous videos, we covered how we can actually change the probability cutoff at any different point in terms of the predicted probabilities, and that can change the sensitivity or the specificity of the model depending on what's our trade-off value over here. So this sensitivity specificity table was generated using C table, and what the ROC does is it's a graphical representation of that same table, but we are plotting sensitivity and 1 minus specificity against the diagonal line, which is the random model. So how does this work? Let's work with our telecom data again, and we've got the predicted probabilities, and we've got whether the customer churned or not in the data set. I'm going to take out these two columns and push them over here. So this is our modeled probabilities. And what I'm going to also do is I'm going to create something known as a random model, which will tell us how would it perform if I didn't have any model at all. So let's call it a random model, and just fill in some random values over here. And this is going to be like my random model. And I've not done any analytics, statistics, or any regression over here. I just simply filled in values between 0 and 1 over here. So this gives me my random model. This is kind of like my reference model, and this is my my logistic model, which I can compare against the random model and figure out how much better is my logistic model performing against any arbitrary random model. So what we're going to do over here is we're going to create something known as the cutoff for logistic, and we're going to do a cutoff for random. And let's start off with the same cutoff. If logistic model score is greater than 0.5, then predict a churn, else don't predict a churn. And for random also, if the random model is greater than 0.5, predict a churn, else don't predict a churn. And there we have it. And let's go all the way down. So now I'm going to create a confusion matrix, one with the logistic model and the other with the random model. So let's go ahead and create a confusion matrix, put churn into the column labels, and I'm going to put the logistic model into the row labels. Let's put in the number of observations in over here, and I'm just going to copy this pivot again over here. Instead of the logistic cutoff, I'm going to just put in a random cutoff over here. And let's create sensitivity, and let's create specificity. And since the ROC curve is sensitivity on one side and 1 minus specificity on the other side, so let's create 1 minus specificity over here. This gives us the cutoff that we're going to use, and we're going to put it over here. So let's put the cutoff in the middle, so we both of the confusion matrix are running off the same cutoff, and the cutoff is 0.5. In fact, I'm just going to go into the formula and change the cutoff. Instead of hard coding it as 0.5, I'm going to change it to the cell over here, so that when I change it over there, it'll automatically update. So let's change from 0.5 to a value over here, and let's launch it throughout. And in fact, I'm just going to change the cutoff to 0.1 for start, and let's refresh our pivots. Okay, so now what's the formula for sensitivity? And we've covered this before. If once we have a confusion matrix, this is the actual state and this is the predicted state. The confusion sensitivity is true positive divided by true positive plus false negative. So let's calculate sensitivity over here. True positive is going to be the churn correctly predicted as churn, which is C6 divided by the total number of churn in the data set, which is summation of C5 and C6. So that's 94%. And specificity, if I look at the formula again, specificity is percentage of actual negatives testing as negatives, i.e. true negative divided by true negative plus false positive. So this is going to be equal to B5 divided by sum of B5 to B6, and that gives me the specificity, and 1 minus specificity is simply 1 minus this value over here. And similarly the sensitivity for the random model is going to be the same formula, so I just apply it over here. Make sure it's running correctly. It's running correctly. Then specificity, same formula over here. Make sure it's running correctly. It needs to be sorted out correctly, so let's run it off. In fact, both of my formulas need to be correctly sorted out. Sorry about that. And 1 minus specificity is equal to 1 minus specificity over here. And there we have it. And what I'm going to do is I'm going to create a table which matches the sensitivities and specificity for both the models. So sensitivity 1 minus specificity. So this is for the model, and I'm going to do the same for my random model as well. So random model sensitivity and random model 1 minus specificity. And let's start calculating this. For point 1, I see that the sensitivity and 1 minus specificity for my model is 0.93 and 0.58 or 58%. For my random model, where I'm not using any model, the sensitivity is 93% and 1 minus specificity is also at 90%. And this is at 0.1. Let's change this cutoff from 0.1 to 0.2, i.e. anything above the score of 0.2 is considered a churned object or churned subscriber. Anything below is non-churn. And let's refresh our matrices. I refresh this one and I refresh this one, and there we have it. Now the sensitivity goes down slightly, specificity rises, so 1 minus specificity actually drops. And let's look at the random model as well. There we have it for 0.2. Let's do this for 0.3 as well. And sensitivity is dropping down to 72%. So let's see. And 1 minus specificity down to 23%. And for our random model, both of them are at 70% sensitivity, 1 minus specificity also very close to 72%. So this was 0.3. Now let's change it to 0.4. Let's refresh this, and I'm going to do it all the way till 0.9. And let's feed in the new values. So 59.18. Specificity at 0.14. Similarly, let's put it over here. and this is 0.4. Let's put it at 0.5 now. Let's change the cutoff to 0.5. Refresh this and put in the values again. Similar structure here. Now change it to 0.6. This is going to take a while, so I guess you can safely skip the video to the next few minutes while I build up this matrix. Sensitivity here, minus specificity here. This was 0.6. Now let's change the cutoff to 0.7. Refresh this. This becomes 13%. This becomes 3%, and this becomes 34 and about 33. Let's change this to 0.8. Sensitivity drops down to 4%. 1 minus specificity also very low, and over here it's 23 and 23. So this was 0.7, this was 0.8, and finally let's change the cutoff to 0. I don't think 0.9 is there's any value above 0.9. There's not. So let's change it to 0.8. I think 4 was the highest that it goes. Nope, so let's put it down to 0.83. Okay, sensitivity at 1.4%, 1 minus specificity at 0%, and similarly we have 21% and we have 19%, and this is 0.83. Now what you will observe is that as the cutoffs change, and this is 1 minus specificity. I've labeled it wrongly. Minus specificity. Now what you will observe is in the random model, depending on no matter what the cutoff is, if I plot this in like a line or a graph, so let me plot this in the manner of a scatter diagram. I get almost a diagonal line going from the lowest to the highest. So this actually gives me an idea. This actually shows me something which can be happening over here. So for example, if I'm plotting, let's go into the middle. If I'm plotting sensitivity and 1 minus specificity, so the y-axis is sensitivity going up, and this is 1 minus specificity on the x-axis going this way. If I look at a random model, what I will see is that it follows almost a diagonal line. The first point is at 90% each, the next is at 80% each, then 70, then 60, then 50, 40, 30, 20, and 10. What you will see is that sensitivity and 1 minus specificity, they follow almost a diagonal line at 45% to the axis, each axis at about 45% each. And this gives you the performance of a random model. If there is, in fact, what you're doing is you're just tossing a coin and figuring out whether the customer is going to churn or not. This gives you the performance of a random model. But on the other hand, if you plot the same graph on the model that we've generated, and you again look at the line that comes out over here. Let's plot it the other way around. So I'm just going to move this over here. So let's plot 1 minus specificity. Sorry. I want 1 minus specificity to be on the x-axis. So that's the reason I've just moved it over here. Let's plot this graph now. And what you will see is a different kind of a shape. It jumps up immediately on the sensitivity side, and the 1 minus specificity side starts lagging. And what this essentially gives us, it gives us a kind of a curve for the model, and I'm going to draw the model with a different line. So the model curve starts going something like this all the way. If this is going to be the sensitivity and specificity at, so the origin is 0 and this is at 100% each on both sides. The random model essentially follows a diagonal line where at each point the sensitivity and specificity are equal to each other, so there is no difference. Sensitivity and specificity at any point is the same value, then it follows a diagonal line going up. But if you look at the model that we've actually built over here, and we are using the logistic model now, and at each point when I compare it with the value of sensitivity and specificity, it's very different. So you see it starts off at 58%, 1 minus specificity, and then 93% sensitivity, and so on. This is following kind of a perfect line, so to say. And if I plot it over here, and what you can see is, let me push this off and let's work with this itself. Does it this way? Well, let's get rid of this. Okay, so what you see over here is almost that the line for the model, it starts going over this curve and starts jumping up until the time it meets towards the end over here. So there is a trade-off that if sensitivity rises, 1 minus specificity also rises, but slowly, or rather the specificity is small. So the more is the difference between the line that we generate from a model versus the random model, which is the line, the better the model is. So for example, if I look at a ROC curve for, this is the random model, and I've built one model which goes something like this, and I build another model on the same data set. This time let's build it on a blue line. All right, and this line goes something like this. Now in this case, if you have to compare the green model versus the blue model, you can obviously see that the blue model outperforms the green model, because the distance between the green model and the random model is very small, but the distance between the green model and the blue model and the random model is much larger. So this gives you the predictive power of the model. And what we are doing is we're essentially generating the sensitivity and 1 minus specificity at different points in the cutoff. So if I keep changing the cutoff for my decision, and this cutoff is being applied on the actual probability score that we've generated over here for the logistic as well as the random model, and this gives me the trade-off between 1 minus specificity and the sensitivity. And the further this graph goes towards the corner of the corner of this diagram, the better it is. And this in a nutshell is the ROC curve. And we always plot the ROC curve against the random model, which is just the diagonal line. Now another statistic that we do look at is area under the curve, area under the ROC curve. And this is also a very simple statistic. Now if both sides have a length of 1. So we know the distance between 0 and 100% and 0 and 100 is simply 0 and 1. We assume this to be unit square of side 1 each. Then the total area of the square is 1 into 1, which is equal to 1 itself. Now what's the area of the square? Area under just the random diagonal line. So this area under just the random diagonal line is obviously 0.5 because it divides the square into two equal triangles. Now the area under the ROC is what's the area total under this whole curve that we've generated over here. The better the model is, the higher the curve goes above the random line, the more is the area under the curve. So what we can do is we can actually compare the area under the curve for the blue line and the area under the curve for the green model, and then figure out which of these models has a higher area under the curve, and that's better. So if the area under the curve starts approaching 0.5, that essentially means it's a random model, because even if I just randomly generate any number and convert that into a probability score, even that will give me an area of 0.5. So that essentially means that model is useless. The best possible model will have an area under the curve of equal to 1. And this is where the C-stat in logistic regression comes into play. So whenever we run this logistic regression model, we get the association of predicted probabilities, and we've already covered concordant, discordant, tied. We've covered Somers D, gamma, and tau C, but we didn't cover what is the C-stat over here. So the C-stat is the area under the curve in the receiver operating characteristic, and we've just figured out how do we actually create this receiver operating characteristic using sensitivity and 1 minus specificity. So I know the maximum possible area is 1. In my model that we generated, we've got a area under the curve of 0.822, and that's the area under the curve on the training data set itself. I can also create this same 1 minus sensitivity and specificity sensitivity and specificity trade-off for my validation and generate the area under the curve and compare it again over here. So we generated the KS stat for both training and validation and compared against each other. Now we're going to do is compare the area under the curve as well. So this is the C stat, which is automatically generated using logistic regression, but we can also use a basic proc rank and proc sequel procedure which calculates the area under the curve over here. So what I've done is what we can quickly do is we can use this simple SAS procedure to generate the area under the curve for the training data set. And what I'm doing is I'm just running this for training data set just to make sure that the area under the curve is calculated correctly. For training, the area under the curve is coming out to be 0.821809. So this is the AUC for training. And this is actually coming exactly the same what you would expect, because SAS has also generated the area under the curve. So if I compare this with the proc logistic output on training day, the proc logistic output also should give you exactly the same C value or the area under the curve, which is 0.822. So for training, the area under the curve is 0.822. And what I can do is now, since I have the data set, I need to score the validation data set, and then I need to run the AUC procedure on the validation to generate the area under the curve. So let's do that. I have the model estimates out. So I'm going to proc score data equal to valid, score equal to this, out equal to v underscore score, type equal to params. Change this to v underscore score. Everything else is the same. So run this, and I get an area under the curve in validation to be 0.79. So this is AUC for validation. Which has come out to be about 0.789. Now in some SAS SaaS versions, you can actually plot this curve as well for both training and validation. Unfortunately, my SaaS is an older version, does not have the capability to plot, but you can explore the ROC option and generate the AUC plots as well. But I've shown you how to do this manually as well. So we managed to create the plots using scatter diagrams. Not the best way, but this is actually the same data set on which the plots are being generated. In fact, if you have the C table output, you should be able to generate the ROC curve as well. So anyhow, what we wanted to see was the area under the curve for the validation as well. This is coming out to be very close. If these two values, just like the K-stat, if there is a large deviation in the area under the curve between training and validation, that can also be a measure of overfitting. Now, one last thing is some people, instead of the AUC of the ROC, like to look at the Gini. The Gini is similar to the area under the curve, which is simply equal to 2 into the AUC minus 1. So this is the Gini for our model for training, and this is the Gini for our model for validation. So both Gini and the ROC curve are almost the same thing. There's no difference between them. It's a matter of choice. Which do you prefer? I prefer to use the ROC curve because it's more intuitive for me, but for others it might be the Gini curve. So one quick recap. So this is the ROC curve. It plots. It's generated between sensitivity and 1 minus specificity for each plot, for each p-value cut point, as we saw over here. Perfect models will see the red line rising from bottom left and going all the way up over here. So perfect sensitivity at almost 0, 1 minus specificity. The diagonal line depicts the performance of a random model or a no model, and more is the difference between the red line and the black line, the better the model is. We always measure the area under the curve for an ROC plot. That's the total area in this square which falls below this red line. And any area of the curve which is approaching 0.5 is typically a random model, because that's what the area under the diagonal as well. So the more the area under the curve starts approaching the value of 1, the better it is. If the area under the curve value starts approaching 0.5, therefore the more weaker the model is. So what's a good AUC? There again, there is no good or bad AUC. Typically higher the AUC, the better the model, and this is more used to compare competing models on the same data set than to figure out whether a model is good or bad. So typically you should be suspicious of very low AUC, i.e. poor performances, if they are unable to beat a random model. And if you have AUCs which are very, very high, that's also an indication that something's gone wrong. You should be suspicious of models which perform too well. In almost all cases, that would mean your data set is wrong. So be suspicious of extremely good and extremely bad models. Gini is almost the same as an ROC curve, and the value of Gini is again 2 into AUC of ROC minus 1. Gini is simply the inverted ROC curve. In the ROC curve, we actually plot sensitivity versus 1 minus specificity. If on the other hand you start plotting sensitivity with specificity directly, you get the Gini curve. So there is no difference per se between them. It goes down to a matter of personal preference. And we've already covered the KS separation. KS separation is the max separation between the cumulative event and the non-event, and that's also a popularly used statistic to figure out how good or bad a model is. So that brings us to an end of our basic series on logistic regression modeling using a case study. In the next few videos, I'm going to cover additional case studies. More specifically, I'm going to focus on the credit scoring data set. And what I would recommend is, after going through all of these videos, you also try out your hand on the Charles Book Club case study. Try to build a model. Try to generate training and validation splits. Look at the ROC, look at the KS separation, look at the Lorentz curve and the lift curves for your data set, and try to replicate what we've done to date. And in the credit scoring data set, I'm also going to use a profitability function to actually come to the the best possible cutoff that we can generate in our data set. So onwards to the next video.